Welcome to everyone. Thank you for joining us this morning. Or could be afternoon where you are. We are very happy to have today in our webinar that is the innovation series, Dr. Khalid Tantawi. I'll tell you more about him in just a minute, but I want to talk a little bit about CREATE and what CREATE is for those who are unfamiliar. You can go to the next slide, Kathleen.
If it'll let me. Okay. Here we go.
Thank you. So CREATE is a national energy center funded by the National Science Foundation. We are focused on helping schools and instructors with their energy programs, helping them with professional development and curriculum development, as well as mentoring. And all of the resources and information can be found on our website, createenergy.org. Let's go to the next slide.
Well, let me. There we go.
Great. We do have some upcoming events that we want to make sure you are aware of. We have face-to-face professional development workshops coming up this summer. First of all, a solar workshop in Madison, Wisconsin at the beginning of July. That is full. There is a waiting list, but there is also a solar workshop in North Carolina that is not full in the middle of July, and a solar plus storage, solar plus batteries, right, workshop at the end of July in Madison, Wisconsin again. The information for those can be found under the events tab on the website. Also, we are having monthly virtual coffee hours. A lot of us that are teaching in various energy disciplines are the only faculty member at our school doing this. And so we found that creating a way for us to be in more regular contact has been very helpful. But we do have a coffee hour coming up on May 13th around recruitment of students, a topic that is something that many of us think a lot about and struggle with. So feel free to join us. We would love to have you for that. Go to the next slide. And then we also have a couple more webinars in this innovations series, these short ones. On April 26th, a couple of energy activities for the classroom, and on May 8th, talking about decarbonization of domestic hot water, or a lab for students to think about that. If you are interested in attending either of these, you can let Gabby know, and her email is on the screen, and that would be great. They will be recorded and posted if you aren't able to attend in person at that time. And with that, let's go to the next slide, and I will introduce Dr. Khalid Tantawi, who is going to be talking today to us. He is an assistant professor of mechatronics engineering technology at the University of Tennessee at Chattanooga, has a PhD in electrical engineering from the University of Alabama at Huntsville, and he also has double masters in aerospace engineering. And I am not going to be able to give the correct French pronunciation of one of those schools, but the Institute for Aeronautics and Space, as well as a master's from the University of Pisa. Previously, he taught mechatronics at Motlow State Community College, and also was a trainer for the Siemens Technique Academy for certifying mechatronics at level 1. He was elected the chair of the engineering section of the Tennessee Academy of Science in 2022, and has been a reviewer for a lot of conferences and journals, as well as a panelist for the Tennessee Textbook Advisory Panel, and is on academic audit committees for the Tennessee Board of Regents. Continues to research in microfabrication and materials characterization, as well as writing things about mechatronics and engineering education. So we are very excited and happy to have him with us today to talk about a student research project on cooling of vehicles using solar. Welcome, Khalid.
Yeah, sorry, Joel, I think I just lost connection.
Oh, okay.
No.
Well, I just finished introducing you, so whenever you're ready.
Thanks so much. Thanks. So let me share my presentation.
Yeah.
Thanks, Joel. Thanks, Kathleen, and thanks everyone for attending. And so this is the webinar, and I'm presenting today a student undergraduate project. Basically, it's a research project on solar-powered cooling system for powered vehicles. These are the students that worked on the project. This is the project being tested. And this is one of the classes that have been working on solar power labs. So first, let me just introduce, or let's talk about the background for this work. So during the hot summer months, the temperature inside vehicles, depending on the location, can reach up to 170 degrees. So now the National Safety Council says that there are 38 heat stroke deaths that result from in powered vehicles. Mainly, of course, it's going to be for children that parents forget them in the car. Now, recent advances in solar cells have allowed them to be more efficient and more flexible, with higher mechanical flexibility, and lighter in weight. So they can be more efficient and lighter in weight and better mechanical flexibility. That allows them to be used for more applications. One of these applications is for powering this application in which we power a cooling system in the parked vehicle. So in this work, we present a solar-powered cooling system with the purpose of cooling parked vehicles in the hot summer months at a peak power of about 80 to 100 watts. You can actually go a little higher depending on the solar panels that you use, but the ones that we used were 100 watt solar panels. So let's look at the system requirements for that and constraints that we put. So the main constraint is that it needs to be something flexible and easy to use. So, like for example, you see this is the sun visor that you can put on your windscreen. So we want something like this, something that is easy, that can be easily replaced and removed. So we want the solar panel to be something that you can mount on the sun visor like this, and at the same time, like I said, ease of use and low cost. It has to be something, it shouldn't be something that will cost you thousands of dollars. So we limited it to be below $100. Now, another thing is that it has to be only solar powered. It's only solar powered. It cannot be powered by the battery. Why? Because you don't want to drain the battery. It must have a high level of flexibility, of course, mechanical flexibility to allow for easy use. And only the windshield area can be used to collect solar power. And again, the reason is because we want to be easily removed and put back so that the person can drive. So in other words, because otherwise, if it's complex and difficult to use, then no one will use it. So these are the system requirements and constraints. Now, let's look at the principle of operation. How does it work? So it's not a fan. It's not only a fan. So there are systems available in the market where you have only fans, but this is a heat pump. It's actually a reverse heat pump. So now let's talk about the reverse heat pump. Basically what it does, it takes heat and it pumps the heat from inside the vehicle outside. So there's a coolant, water, or antifreeze that circulates. Of course, antifreeze is better because it can collect more heat than water. Now, there's a coolant block. Basically, it's a heat exchanger that is mounted outside the vehicle, and the heat exchanger is mounted on the window like you see over here. And it's connected to something called a Peltier device. A Peltier device is this over here. Now the Peltier device what it does, if you connect it to power, this side becomes, for example, this side becomes extremely cold, like freezing cold. And this side becomes extremely hot. It will burn if you touch it. So what it does, it takes basically the heat from this side and it pumps it to this side, to that side over here. This is the Peltier element, and this is the main heat exchange. This is the main one that is used for heat pumping. Now, so the water circulates over here, or the antifreeze circulates on this side. It gets cooled down, and the heat is taken from the water or the antifreeze and it's pumped on this side. Now, this side over here, there is a heat sink, an aluminum heat sink that is mounted here, and a fan to dissipate the heat away into the environment. And that's why it's mounted outside the vehicle. Now, inside the vehicle, there is another heat exchanger. The heat exchanger into the vehicle is actually a radiator where the water or the antifreeze, the cool antifreeze circulates. And there's a pump, of course, a small pump that pumps the antifreeze, and there are fans. So the fans basically they make the air in the vehicle. They push the air on the radiator so that it does a heat exchange and it becomes cool, and it will push the air inside the vehicle, the cold air inside the vehicle. So this is basically the two heat exchange mechanisms that take place. So this is how it pumps heat from inside to outside. Now, this is a video, but unfortunately it's not working. I've been trying to get the video to work here. But anyway, this video shows one of the first prototype that we had, which basically, as you see here, this is the heat exchanger, the water block, and this is the heat sink, and these are the fans, and actually it's over here. So this is the system basically. So this is the system over here, and this is the part that is outside the vehicle. So this is the heat. This is the heat exchanger, the water block, and sandwiched between this and the heat sink is the Peltier device, and then we have the heat sink and the fans. Then, so now let's look at the heat exchanger that is inside the vehicle. Now, actually, let's talk more about this. So here, basically, the water comes in hot from inside the vehicle, and it circulates here, where heat is taken by the Peltier element, and the heat is pumped to that side over here, the side where there's the heat sink. So and then the heat sink, basically there are fans that dissipate the heat to the air. So this is the heat exchange that takes place outside the vehicle. I have to give credit to the students because they came up with all this mechanism. They researched, and I helped them because I gave them guidance on how what basically has to be a heat pump and how the heat is pumped. But they did the research and they actually came with this mechanism using the Peltier device. Now inside the vehicle is this heat exchanger, which is simply a radiator. So it's this here. It's basically a radiator, and there are fans on one side. And so what happens is that the cold water, after it has been cooled from outside, it comes in from here and it circulates into this radiator where the air is blown on it, and basically, and you have a stream of cold air coming out. So this is basically what takes place. This is the two heat exchangers. Now, let's look at the power. So we have seen how the system works, the mechanism. Now let's talk about the power. Like I said, the limitation is that you have to use only the front windshield, the windshield area. And it has to be the area, of course, now this here is for a small vehicle. So this is the area that you have. So now, what we have used to test the system, we have used these solar panels. We have used 4 of these. These were granted to us by the Create Center. And so we tested with these, and of course it ran perfectly. Now, then we tested, because of this, I mean, you can't make them, it's not going to be easy to use them, so we have to use a solar panel that is flexible and that is smaller, let's say. We tested this solar panel, it has a high level of flexibility, but still it's large. Now, so what we are now doing, we purchased these here, this solar panel from Alibaba, or actually AliExpress. It's like $30, and this solar panel is, as you see, it's small. You can use actually 3 of these. You can put them together, and it's foldable and lightweight. So this can give about 40 to 50 watts. So in other words, if we use 3, we can get around 100 to 150 watts, which is good. So this is basically the current stage, what we are doing. And we try to test these. We also purchase these small solar power strips, photovoltaic cells, but these are, I mean, these had actually, let's say, these are a lot more expensive if you want to buy them, and it's going to be a lot more work to do. So this is the solar power. Now let's look at the power budget. So the power budget, basically, the main element that takes most of the power is this Peltier device, the one that really does the cooling. So this here takes between 50 and 70 watts, like about 80% of the total power. Everything else, all the fans, the pump, they all take together 20 watts. So generally speaking, it's really, I mean, this here, really the cooling part really is the one that takes most of the more, of course, the better. But we only can put one or two Peltier devices. So now, so in total we have about 80 to 100 watts. And now let's look at the main question that is on everyone's mind, which is, how effective is this system? Let's look at let's see the effectiveness of this system. Now, before we do that, let's first talk about the regular air conditioners for vehicles. So for a small car, believe it or not, the air conditioner takes 5 horsepower at full strength, at full capacity. When you turn it to full power, it's 5 horsepower. For a minivan or pickup trucks, it can be probably 17 or 18 horsepower. So if you have like a car that is 100 horsepower or 120 horsepower, there's about like 5% of its power, of the engine power, goes to air conditioning. And if you have a small car and if you are going up the hill, for example, if you turn on the air conditioner, you might notice that the engine power went down slightly. It's because the air conditioner takes a considerable amount of power. So at full capacity, we said it's 5 horsepower. Now here we have a 100-watt system. Now if we assume an efficiency of 50 to 80% of the Peltier element, then it can be shown with calculations that you can get about, so the effectiveness is going to be about 1.6% of an air conditioner running at full capacity. Okay, it can vary if you run it lower, like half or third of the full capacity. We can go like up to 6 or 7%. All right. So 6 or 7% of an air conditioner is, let's say, at this level, the system cannot support life in the vehicle under the sun, and it shouldn't be used to support life, but it can increase chances of survival. So if you use it, it's going to increase, it can give some more time, it can increase chance of survival for a person inside the vehicle under the sun. And it may provide sufficient transient thermal comfort when blown air is in direct contact with the occupant. So this is the system. And these are the students when they presented the system. And in the next class, I will try to make improvements and we're gonna make this will get smaller radiator than this. This is a little too big. Of course, that's gonna be more pricier. And also we're gonna get smaller tubes so that it can become smaller and more easily more flexible. And we're gonna, like I said, we're gonna use these solar panels and mount them on the sun visor so that it becomes also, to increase flexibility. And we are actually working on filing a patent for the system. There's no system available in the market. We researched about that. Like I said, mostly are just fans. Like you have like solar powered fans that circulate air, but none actually uses a heat pump. Now, another thing, just one last point, is efficiency. How can we, like you can, for example, we saw there are two heat exchangers. There's a radiator inside and there is the Peltier element outside. Now, the question is, can we exchange them? Can we like replace them? Can this be outside and the Peltier element inside? The answer is yeah, you can. But for efficiency purposes, the best efficiency is to put the Peltier element outside because remember that it consumes up to 70 watts by itself. So 70 watts, it needs to get rid of the 70 watts. The best way to get rid of it is to put it all outside so that it's dissipated outside. Thanks. And if anyone has questions, you're welcome to.
Fantastic. Thank you, Khalid.
Thanks, Joe.
Yeah. Are there questions that anyone has right off the top? Oh, Khalid, I had a couple questions. I can prime the pump here for other people to think about this. So what class were you having the students do this research in?
Yeah, so actually there are two classes. So first we have a class on applied power systems. They worked on a part of this, but the main class is maintenance, is the maintenance class, maintenance of mechatronic systems. And this is basically a class where they take projects as the lab and they work on them. So they actually work on this project. But I have also to say there's also the electrical circuits class. We have electrical and electronic systems class. It's now the year levels of the students. First year is they take electrical systems. Third year they take second and third year they take the maintenance and the applied power classes.
Okay.
Thanks.
So it sounds like you had students, or at least certainly leading up to this project, but also developing the project over several classes. It's very interesting. Yeah. We at Madison College, we have a class that's kind of a capstone class for the engineering program where the students are given some problem and they have to come up with a solution for it, through testing out various
we also do
options.
have capstone classes. But the main class I actually give in this is in the maintenance because the class basically there's no textbook in the class.
Yeah.
And they just really like learn different systems. So they have a sufficient amount of time to work on a project.
Sure. And did you have different groups within the class working on different possibilities?
Different groups. But they worked on different projects, like different other projects.
Okay, all right.
Yeah.
So this is one of them. Got it.
Mm-hmm. Yeah.
And did they come up with other ideas before they came up with this one?
Yeah, so there were several ideas. Let's say, but the main thing was to use a heat pump. I asked them it has to be, whatever idea they use, but it has to be a heat pump. Now, for example, one idea was to use just like the home air conditioners do, basically where you have a coolant that expands and compressed, but that's going to be a lot more difficult. And that's cannot be, it's basically cannot be done on a small scale. And the smallest scale possible is to a heat pump was actually using the Peltier devices, which is actually, by the way, it's the same. It is used in cooling the CPUs for computers. So the coolant for some computers actually use similar mechanisms. And that was a good idea. A student came up with this idea, and it was very good.
Great.
So I mean, they had the opportunity to research, which is, I mean,
Yes.
the really good point, and you'll be impressed at how the students they research. They do excellent job, and when they put effort, they do excellent job, and they come up with very brilliant ideas.
Yeah, nice. Yeah, it is. It's, you know, it's something that a lot of times we don't see at undergraduate level, like being able to do research and test things out. So it's a really nice example that you have here.
Yeah, thanks. And I think it's this is one good thing about the class is that it gives them, because there's not much, like I said, there's no textbook, so there's not much of let's say, I mean, they don't have to. There's no. It's really, I mean, it pushes them to engage in projects, in
Right.
researching, and gives them sufficient time to research and engage in projects in real time, I'm sorry, real life projects that can solve real life problems.
Nice.
Thanks.
Any other questions or comments that anyone has? So you're going to then take the results of this class and bring it next year, have them work on improving it. That's what you were saying?
Yeah, so yeah, it needs some improvements. Yeah, like I said, I mean, it's really, we're gonna let's say the main thing is to increase flexibility, increase flexibility of the system, because it's right now at this stage. I mean, if you look at the pictures, it lacks that thing. I mean, the flexibility part. You can see here, for example, this. You see this how bulky it is. So we're gonna have to. The first thing is we're gonna have to replace this and the tubes. The tubes are too thick.
Mm.
And so we need a radiator that's smaller, let's see, and basically to be more flexible. These are mounted. I mean, it should be like permanently mounted on, not permanently. I mean, like they can be mounted on the windscreen, on the side, the passenger side, and left, and then you can just connect. When you get into the vehicle, you just put in the solar panel, and you just plug it into this system, and it will start running. This is how it's, I mean, it's supposed to be working.
Sure.
Yeah. And really, I really like to leave the students, and they improve it on. I mean, I just don't give them hints, or I mean, like I give them my own opinion, and I give them the freedom to change whatever they want, because I really like the ideas that they come up with. They can they usually, most of the time, they end up giving me a project that is way better than I initially imagined it. And this is, I mean, this is the main thing that I like. I like to give them the freedom to change however they like. And sometimes, of course, they may fail, which is fine. But I mean, the success is usually great and a lot better than I would be expecting initially.
That's great.
And I have to thank the Create Center for giving us the solar panels and several other equipment actually you provide to us. They have been really critical for this course. And actually, this is how I really initiated this project after visiting the Create Center and went to the workshop at the Create Center. And it was I had several ideas actually from that. And as you see, the students are they use them, and they're happy with that, and they learned a lot from providing this equipment. So thanks.
Fantastic. Yeah, that's great. That's a great validation. You know, we know from the front side, we heard from teachers that being able to get equipment would be really useful, but it's great to hear the story of it being used and how well it worked out.
Thanks, Joe.
Well, we are at the end of our 30 minutes. If there are any last questions, we can take them.
I don't see any. Chris Miller did a thumbs up and then he had to go, so.
Okay, fantastic. Thank you, Kathleen.
All right.
Well, thanks again, Khalid, for
Thank you so
sharing
much.
this, fascinating project and sharing, this research opportunity you give with your students. It's quite inspiring. So thank you very
Thank you so much. Thanks.
Thank you.
Thanks.
All right. We'll see everyone.
Have a good day. Thanks.
You too.
See you. Bye.
Bye.
Thank you, Kathleen.